In the realms of theoretical physics, one of the most ambitious and captivating ideas that has emerged is string theory. String theory is a framework that attempts to harmonize the equations of quantum mechanics, which rule the subatomic world, with general relativity, the principles guiding the cosmos at massive scales. These two foundational components of physics have been historically at odds, but string theory presents a potential solution to bridge the gap between them. To understand string theory, one must move beyond the concept of point-like particles, which constitute matter in the standard model of particle physics. Instead, string theory proposes that the fundamental constituents of the universe are not zero-dimensional points, but one-dimensional strings. These strings can either be open, like a segment with two distinct endpoints or closed, forming a loop with no endpoints, and they vibrate at different frequencies. It is the vibrational patterns of these strings that give rise to the particles and forces we observe, much like different notes emerge from the strings of a musical instrument. String theory significantly expands our concept of the universe. It requires extra dimensions of space, beyond the familiar three dimensions of length, width, and height, plus the dimension of time. Depending on the version of string theory, there could be as many as 26 dimensions. However, the most prevalent form, known as superstring theory, suggests 10 dimensions. These extra dimensions are believed to be compactified or curled up so small that they are imperceptible at human scales or with current technological capabilities. Another surprising feature of string theory is the existence of supersymmetry, a theoretical symmetry between the two basic classes of particles: bosons, which carry forces, and fermions, which make up matter. This symmetry suggests that for every known particle, there is a superpartner particle not yet observed. The mathematical complexity of string theory is both its strength and its challenge. It has led to remarkable insights such as the holographic principle, which proposes that some descriptions of a volume of space can be thought of as encoded on a lower dimensional boundary, inspiring new ways of thinking about black holes and the nature of gravity. Nevertheless, string theory is not without its criticisms. As of now, it remains largely untestable. The energy scales at which string effects would become noticeable are so high that current particle accelerators cannot reach them. This means that many predictions of string theory are, for the time being, beyond our grasp to validate experimentally. Critics argue that a theory that cannot be empirically tested does not qualify as a scientific theory in the traditional sense. Despite these criticisms, string theory provides a rich theoretical framework that continues to guide researchers in their quest to understand the fundamental laws governing everything in the universe. It is a work in progress, an evolving theory that is part of the broader endeavor in physics to find a unified theory of everything, a single, cohesive framework that would explain all physical aspects of the universe. While the journey is complex and fraught with challenges, the promise of string theory remains a beacon for physicists searching for the ultimate principles that define our reality.